Good evening. It is Monday the 19th, and today we're talking about lists. So I'm a little late on this, that's my bad. But, lists is a abstract data type that we cover in this class. So we're going to cover a couple different levels of abstraction with our lists. So the very top one is just understanding what this abstract data type is and how it works. The next one is we look at the actual list data structure that we'll probably be using. Then we look at the implementation and then the code to implement it. So, at the very highest level, a list is a sequence of items, just in a specific order. A list has operations. We can append, remove, search, print the list. Some linked lists support sorting. And there's a lot of different implementations of lists, but for this class we talk about singly linked list and doubly linked lists. So in class, uh, to sort of visualize what a linked list is, I brought up the game of telephone. So in the game of telephone, we have a line of people. So I'm gonna draw a couple, and each one has a person that comes after them. So this is Bob. Bob is going to say whatever the secret phrase is to Linda. Linda is going to say it to Jerry. And Jerry is going to say it to Steve. So if I want to, include myself into this game of telephone, well, I have to put myself in the list somewhere. So let's say I want to be right here in between Linda and Jerry. Instead of having Linda talk to Jerry, I'm going to cross that out. I'm going to have Linda talk to me, give myself a smiley face, and then I will talk to Jerry. And it's that simple. That's the basic idea of lists. So, a couple different data structure or operations you're going to see with lists and most other ADTs are these. It's going to be stuff like is empty, get length, have a couple ways to add or remove from it, so append and insert after. And then we have remove, search, sort, print, and maybe a print in reverse. So, at the core of a linked list, each element in it is going to be called a node. The node is going to have a value and a pointer that is called next. We also include two pointers in the overall list. One is called head and one is called tail. So, if I were to turn these people into nodes, I'll make a Bob node, for example. So, Bob is going to be the head of my telephone game. So, this is Bob. I was going to draw a node for him, actually. So, we have Bob as the value. Now, Bob's next pointer is going to point to Linda. So, value is equal to Linda. Linda is going to point to Brandon. And I'll cut the list short. And then since I am at the end of the list, my next is going to point to null. So null is a weird keyword in C++. It's basically setting something to nothing, or to zero something out if that zero was nothing. It's worth digging into if you're interested, but for now just think of it as nothing because it's null. Then in this linked list, I am going to be the tail. So this is your basic visualization of a linked list. It has a head variable, a tail variable, or a pointer, I should say, and then nodes within it. These nodes will all follow the same build. So if you ever see me draw it out, it'll look like this. So inside is going to be some sort of value, and then this is the next pointer. I believe next slide shows it off, but yeah. So the head of this linked list is going to be value 84. all three of these are nodes. 84 points to 6, 6 points to 21, and if I move my head, 21 points to null. The head is set to 84, the tail is set to 21, and yeah. So we have a sort of chain of nodes, or you could even think of this as like train carts on a train. They're connected, and the only way to go is forward or down the line. So why do we use linked lists? So a correctly implemented linked list is super fast. Its insertions and deletions can be done in big O of constant time, which is insane. The one disadvantage is if we want to search the list or work our way down it, we have to do this in linear time. So let's say our telephone linked list didn't have a tail. If we want to get to the end of the list, we have to start at Bob, say, okay, is Bob pointing to null? Nope. So we scoot down and we say, hey, is Linda pointing to null? Nope. So we scoot down. So finally, we get down here and we say, hey, is Brandon pointing to null? And if we are, we know we've hit the end. So if the tail doesn't exist, it's slow, definitely. So now we can start digging into the implementation of it. We look at the algorithms of operations and the pseudocode. So a singly linked list is a data structure that we use. It has a node that has a value, and then that node also points to the next node. Sometimes has a head pointer and a tail pointer, but either way, you're always going to have a head value. So a correctly implemented linked list is more efficient than an array or vector. If you'll remember back when we worked with those, if we wanted to delete somewhere in the middle, so if I wanted to get rid of Linda, I would have to delete Linda in my array. So let me build one out real quick. So we have Bob. I'm going to shorten it. So Linda, let's say a Ricky, and Jerry again. Jerry's back. If we want to delete Linda, we have to first navigate to index 1, position 2. And then we have to move everything down 1. So we delete L. Then we say, hey, R is now in position 1. J is in position 2. Index 1 and 2, my bad. And then this spot, the last spot, will just be null, or maybe we have more data we have to bring in. So that's a lot of operations to delete a single element. So we can start looking at code for a linked list. This is the exciting part of the lecture, right? So normally we're going to have a linked list class, which either has a list node struct or class inside of it as a private attribute. The linked list class itself will have the head and tail as pointers, and then the list node struct is going to have the value and the pointer. Next pointer. So this example has list node as a struct, and inside of the list node we're going to have some sort of value. In this case it's a double, and then we're going to have another list node that called next. This one points to the next list node in the entire list, and it's how we navigate. So we can go look at some of the code for this. We are going to look at list node struct. You do have access to this code if you do want to look. So taking a peep at our linked list.h, we have our linked list class. We have a struct list node as a private attribute. This list node has a value and a pointer to a list node. And then outside of our struct, still private attributes, we have a head and tail list node pointer. And then here's all the fun operations we had. So looking at linkedlist.cpp, we're going to walk through some of the code. So for isEmpty, we're just going to say, hey, does the head pointer exist? Is it not pointing to null? If it is pointing to null, we return false. And if something is there, we return true. to get the length of our linked list, we are going to walk down it until we either hit the tail or we point to null. And for every node that we step over, we increment. So, not too bad. We can see node pointer is set to head. In the actual while loop, we say node pointer is equal to node pointer's next. So if we were here, we'd say, hey, the pointer that I have pointing at Bob, so node pointer is currently equal to Bob, or it's the value of Bob. Whenever I say node pointer is equal to node pointer's next, it says, hey, I'm gonna get rid of some of these arrows. So instead of pointing at Bob, we have to point at whatever is next after Bob. So our node pointer gets shifted to Linda. So this is going to be our node pointer. So all we do is walk down until we find the tail, and then increment. That's going to be a major theme with linked lists, is starting at the head and just walking our way down until we find something, whatever we want. If we want to get a node value at a certain position, we're going to create a node pointer, set node pointer equal to the head of our list, and start walking. While node pointer is not equal to null, so while we haven't hit the end of the list yet, and position is greater than or equal current position, so what if we haven't hit what we're looking for yet, we walk. So current position plus plus, and then node pointer is equal to node pointer next. Whenever we do find the position, we return node pointer's value. So we walk down the list until we count out how many steps we take, then we grab the value. To append to a linked list, this varies on whether or not you have a tail pointer or not. So if you do, what's going to happen is we're going to say, hey, make a new node pointer, create a new node so we can insert into it, set value equal to num and next equal to null, and then we're going to go to tail, and we're just going to say, hey, tail's next is equal to new node, and then we set tail equal to new node. So we update what the last element is. We wanted to add a new node up here. So we're going to walk, or actually no, I lied. We have a tail. So we go to tail and we say, hey tail, you now point to Jimmy, the Jimmy node. Jimmy node points to null. And then all we have to do to finish is scoot tail down. So tail is equal to tail's next, and then tail sits here. The reason that works, so whenever we set memory, so we say, tail is equal to the Brandon node, so OX, we're going to say 10. So OX10, we say, hey, what comes after OX10? So, tail next. It doesn't have to be side by side in memory. Tail's next could be equal to OX 7000 or something like that. And because we're working with memory, we can change, what tail is pointing to. So up here, and tail's next will stay the same until we override it. So by saying tail's next is equal to OX 700, this is still working with OX 10's next. So if we come over here, we say tail's next is equal to new node. So we say, hey, OX 10's next is equal to OX 7000. Perfect. So now that that memory is set, we can say, hey, tail itself is equal to OX7000. And then since we walk tail down, currently we have tail set to OX7000. And then we haven't set the next for this memory slice yet. So if we say, hey, what is Jimmy's next? So tail next, well, it's going to be equivalent to null down here. It takes some time to wrap your head around it, but once you do, it's not terribly painful. So what if we want to insert into a specific position? Well, we're going to need a node pointer to walk down the list, and we need a new node to insert. So we're going to say, hey, starting at the top of the list, the head node, we're going to walk down until node count, or while node count is less than position. Whenever node count is equal to position, so let's say I'm running out of stuff to do this. So let's say we want to insert into Linda's position. We walk until node pointers. I'm going to clean this up. Node pointer is pointing to Linda, and counter is equal to position. So node count is equal to, we'll say 2. Once node count is equal to 2, we break. Then we come down here and we start changing what we're pointing to. So let me get a little bit of room. So we want to insert into position 2. So what we do first is we say new node. I'm running out of names, so I'm just going to say Peter. The Peter node, we're going to point Peter's next to Linda's next. So what this is going to do is it adds an arrow that points to Brandon. Next we have to say, hey, Linda's next is equal to Peter. So we take this arrow out, no longer points to Brandon, and instead it comes down here and points to Peter. So the code is the more intimidating part of this, because once we are in position, all we have to do is change arrows. And then if we want to display a list, we just walk down the list with node pointer and print out the values. The final operation is delete node, and this is probably the trickiest. If we want to delete a node, we have to create 2 nodes. One is one step behind, and it points to the previous node. So node pointer is going to point to, let's say, index 2 in our list. Previous node is going to point to index 1, so we know where we've been. After the edge cases, so if head doesn't exist, if our list is empty, we can't delete anything. If the head of the list is what we're looking to delete, we have to update the head. And then finally, we walk down the list until node pointer, its value is equal to what we're looking for. And once we're there, if node pointer exists, we say previous nodes next. So I got to pull out the chart. I'm sorry. So if we want to delete Linda, Linda's just getting all the hate today. We're going to have previous hovering Bob. We're going to have node pointer on Linda. So we're going to say previous nodes next is equal to node pointers next. So that's going to say, hey, Bob, you now point to Brandon. And then we delete node pointer. So whenever we delete Linda, all of the connections are gone that Linda was pointing to, and now we just have Bob pointing to Brandon. Once we delve into doubly linked lists, it'll get a little more complicated, but not too much. So, oh, I should probably run the program, shouldn't I? So if we want to search, it's not bad. We just walk down the list until we find where node pointer's value is equal to num, and we return where it is. To destroy our linked list, we start at the head, we walk down, and we delete. So, while node pointer is not equal to null, we say next node is equal to node pointer's next. We delete node pointer, and then we set node pointer equal to the next node that we prepared. And we just prep, delete, I guess it would be this way. But we prep, delete, step. That's all it is. So looking at driver.cpp, it's going to add a bunch of nodes, show off is empty, get length, display the list. We're going to search for a couple of values, get value, delete a couple of nodes, and display the list. So let's get that queued up and running. So single linked list with list node as a struct. So starting at the very top, right now the list is empty. Somewhere, we add 3 nodes to the list, 2.5, 7.9, and 12.6. So we take it, we add some nodes. So we have a 2.5, 12.6, it was 7.9 second, wasn't it? Man. At 7.9, and that points to 12.6. 12.6 now points to null, and our list is created. So we can look at what node is in position 1, which would be 7.9. We can search for something outside of the list. A node with value 20.4 could not be found. If we try to search outside of our list size, it's going to complain. And now we can start working with the list. So if we delete 7.9, what we have to do is we're going to have the previous and the current. We say previous next is equal to current's next. I can spell. Good lord. So what this is going to do is point 2.5 at 12.6, and then we get rid of all of the insides. So we deleted 7.9, we're going to insert 9.4 into this. So what happens is we create a node named 9.4. We navigate to, I believe, right here. We say, hey, node pointers. I'm blanking, I'm sorry. We say new node, so 9.4. New node. We set its next equal to current node's next. So we get this arrow fixed, and then we say current node's next is equal to new node. So we get rid of this over top arrow, and we point 2.5 to 9.4. Outside of that, we delete a couple more nodes, and then our list is empty. So, not bad. You can also do the same thing with classes. Instead of having list node as a struct, you can have it as a class. I'm not going to show you the code for this because it's the exact same, except it's now a class. But the cool part about linked lists is you can template them. So if you'll remember back whenever we covered templates, I always bragged on them and said, oh, this is the coolest thing ever. Yeah, you know, if you learn one thing, learn this. This is why. Instead of having to create a lot of different linked lists for a lot of different types, I think it's this one, we can instead template type name our linked list and use that instead. So we have a Booyah template. So in our list node, it has a Booyah value. If we were to return, it would be Booyah get node value, unsure why it's commented out. And then for every single function, it's going to be template, and then in alligators type name Booyah. We add the linked list with type Booyah in alligators, colon, and then our function name. We repeat this, keep going. Guess we do not have a get node value, so comment that out. Looking at the driver, we create a double linked list by saying linked list and then putting the type in alligators. So in this case, double. And then we can work completely with double values. We can append 2.5, 7.9, 12.6. I'll show you we can work with integers also. It's going to drop the decimal spot off of it. So change to single linked list, template no tail. So since we said, hey, it's an integer now, we get 2, 7, and 12 instead of 2.5, 7.9, and 12.6. And then also, since this one only has a head value, I wanted to show off how we would append. It's not that, it's kind of gross. So instead of going straight to our tail, instead we walk down the list until the next value is null, and we know we've hit the tail. And then we can append to the end of the list. So that is the structure template class. I forgot to go with this slide, that's my bad. And now that we are masters at linked lists, we can change to doubly linked lists. It is the exact same thing, except we now have a previous arrow. So instead of just having the front-facing arrow called next, we now have a backwards-facing arrow called previous, whatever you want to call it. But in this example, we have our head and tail, so 84 and 21. 84 points forward to 21 and backwards to null. The value 21 points backwards to 84 and forwards to null. With a doubly linked list, you do have more arrows to change. The operators, more or less, are simple, and you can get away with a lot cooler stuff with a doubly linked list. Instead of just being forced to... Okay, wrong side of a rant. I know with a couple of sorting algorithms being able to work back and forth between the list and not having two pointers, you know, a previous pointer and a current pointer, it makes life so much easier. So if we look at the code for a doubly linked list, we have a next list pointer and a previous list pointer. I'm gonna crack open the code for this to kind of show it off. It's somewhere here. So looking at the linked list.h, we have a struct list node next and a struct list node previous. Once again, you don't have to be locked into structs. You can use classes here if you want. But looking at the code, I believe it is delete node. Yes. Nope, that's display list. I lied. So, more or less, these are going to be the same until we have to start updating the previous. So, if we take a look at append node, we're going to go to the end of the list where tail is. We set tails next equal to new node. We set new node's previous equal to tail. And then tail is equal to new node. So we're just setting everything like normal, but we have an extra line to go backwards. For insert, we create a new node, we walk down our list. So while node pointer is not equal to tail and node count is less than position, we walk. And then down here we say new nodes next is equal to node pointers next. New nodes previous is equal to node pointer. So we get the forward set, we get the backwards. So let's say this is a doubly linked list. Same numbers. So these point to each other. We want to insert 9.4. So we have to set 9.4's next equal to node pointers next. So node pointer is going to be on 2.5. We say, hey, I'm calling this one Jerry. Jerry's next is equal to node pointers next. We say Jerry's previous is equal to node pointer. So we get this forward arrow set and this backwards arrow set. Now what we have to do is go through, we say node pointers next is equal to new node. So we delete this forward facing arrow off of 2.5 and point it to Jerry. Next we have to go to 12.6. So if new nodes next exists, so if we aren't at the end of the list, we say node pointer is equal to new nodes next. If I can, my pen will work. So we scoot node pointer over to 12.6. And then we set node pointers previous to point to Jerry. So while it does add another couple of lines of work, doubly linked lists aren't that bad. If we want to delete, we have to go through, delete everything like normal, make sure the previouses are set. Yeah, that's about it. My one complaint is this code doesn't do anything with the previous. It's kind of lame. Let me take a peek at linked list with sort. This does not do it either. So, all this cool stuff and no examples to show for it. What a teacher I am, right? So, finally, now that we've learned the interworkings of linked lists, we can discuss the C++ standard template library version of list. So the STL provides a bunch of code that was written by smarter people than me that we can use. The three big things are containers, iterators, and algorithms. Containers are class templates for objects that store and organize data. You could say that they contain the data. So we have a list of containers. There's on paper two containers, or two different types of containers. Realistically, there's three. So we have the normal sounding ones, an array, a deck, forward list, a list, and a vector. These two down here have a special name that I forgot, but these set and multiset, map and multimap. It's essentially key value pairings, but that's beyond the point. But arrays, decks, forward list, list vectors, all of it stores data. We have adapter container classes, which are actually the next couple of classes. Let me rephrase that. We have the adapter container classes, which will be the topic covered in the next few lectures. There we go. They're not really containers, they can't stand by themselves. It's more of an implementation idea. So, stuff like stacks and queues, we just augment how the container works. So, these adapter container classes rely on normal containers, arrays, lists, etc., to operate. More on that in a future date. An iterator, it's a pointer. It's used to iterate through a linked list or some sort of other container, and we can access it more or less like arrays. And then finally, we have algorithms. If you ever use this definition of an algorithm, I'm shoving you into a locker. But algorithms are function templates that perform various operations on elements of containers. So, if you want to use, actually, give me a second. Who knew I could yap this much? If you want to use this pre-made list, you have to do pound include list, and then to define it, you say list, give it a type in alligators, and then name your list. This works exactly like a linked list does. Crazy. So a couple different terminologies. You can do a push back and a push front, which either appends or prepends a value. So if we were to push back duct tape, zip ties, and magic erasers, we have everything. Ignore the Sharpies for now. Head would point to duct tape points to zip tie points to magic erasers point to null. If we were to prepend Sharpies, we'd go to head, we'd add it in, and we make sure to update what Sharpies points to. So after we prepend Sharpies, we'd get Sharpies, duct tape, zip ties, and magic erasers. You can do a dot front operator, which just looks at the first node of our list and prints the value. Likewise, you can do a dot back, which will look at whatever tail is pointing to and print it. You can do a dot size, which is going to walk down the list and count every node that it finds. If you were to do a dot size on this list, it would give you the value 4. You can pop back, which will delete the last element in your list. In this case, it would be magic erasers. It has to update the tail and update where everything is pointing. And then this will decrease the list size. So instead of being 4, this list would now be 3. You can pop back again, get rid of zip ties, and then you can also pop front. This deletes the first element in the list. And so if you've been keeping track of our list through all of this, we only have duct tape in it now. If you want to delete items from your list or your templated list, you can do a dot remove value. This is kind of the scorched earth option because it will remove all occurrences within that array. If I have, or not array, linked list. If I have a list of birthdays or birth years maybe, and I say dot remove 2000, it will remove every single node with the element or with the value 2000. So be careful. For an example, we have list.cpp. If I can find it, there it is. So stl. So this just shows you the code of everything we just talked about. We're going to push back a bunch of things, push Sharpies to the front. We get dot front, which will return the string at that node since we're working with strings. And then with that, you can do the dot length. So we get the size of Sharpies, or the length of Sharpies. You can do useful stuff.back to look at the last element, which should be zip ties. You can delete zip ties from the list using pop back, pop front to delete Sharpies, and then I'm gonna uncomment this, but this dot remove will get rid of the other set of Sharpies in our list. So we get the characters in zip ties, no, Sharpies. Duh. So we have 8 characters in Sharpies. The last element is zip ties. Current size, we have 5. We pop, we get 4. We pop front, we get 3. And then we remove the last zip tie, and we have 2 elements in our list. Working with iterators, I don't want to say I've never done it because I've done it in class, but I'm not 100% confident in it. So if you are confident, I would suggest looking up and researching how to work with it. But if you want to be able to iterate through the list, how we do... Let me back this up. As a user, I want to be able to navigate the linked list that I made with the standard template library. To do this, I can use the iterator object that the STL provides. So the iterator is going to start at the head of our list and work its way down as we tell it. So the iterator allows us to add elements, move or remove from where that iterator is positioned. The list has 2 iterators built in that point to the beginning and the end of the list. You could call it a head and a tail. Wonder where you heard that from. And to access the element value that the iterator is pointing to, we just dereference the iterator, so it's exactly like a pointer. For this, we have list with iterator. Let me get that crack open. So we have the same list, but this time we are going over it with iterator. So we get to use a for loop for this, actually. So we say my iterator is equal to useful stuff dot begin. If we wrote it ourselves, this would be equivalent of saying the dot head or the pointer to head. And while the iterator is not at the end of our list, we are going to increment iterator. And then I'm going to add another cout statement here. Hopefully it works. Just going to cout my iterator. And if it doesn't, sad day. We're not going to do that. But we're going to go ahead and run this, and it's going to print every element in the list. So list with iterator. List with iterator round 2. And so we print the front of the list, which is Sharpies, the end of the list, which is magic erasers, and then using the iterator, we are stepping through and printing every element. So it will start at Sharpies, which is at the front. We increment it. It is at duct tape, increment, zip ties, increment, magic erasers. And then my iterator is at useful stuff.end. So we stop. Then last thing, I know, 45 minutes of just pure bliss listening to programming. Whenever we use the iterator, we get access to .insert and .erase. So erase is a removal element that only does a single iterator, or a single node in our list. There's 2 different types of it. You can pass in a single iterator position or 2 iterator positions. This is the difference between deleting a single element or a range of elements within your list. Finally, we have list with insert erase.cpp. Then looking at it, we're doing all the same stuff. We print our list, and then we come down here and we can start adding and removing. So we set my iterator equal to useful stuff.begin, I just realized I never told you how to initialize my iterator. So list string colon colon. We're pulling from the iterator class in lists, and we're calling it my iterator. So we set my iterator equal to the beginning of useful stuff. We increment it twice. So if we're pointing at head, we take a step, we're pointing at the second position, take a step, we're pointing at the third position. In the third position, we're going to insert stapler. We print everything, and now we want to get rid of items. So iterator at the very beginning, we take 3 steps, and we do a dot erase on it. Print everything one more time, and we're golden. So G++ list with insert, and we run it. So before we do anything, we get Sharpies, duct tape, zip ties, and erasers. We insert stapler. So we iterate to the third position and insert stapler there. Print everything, move to the fourth position, so zip ties, and we delete zip ties, rest in peace, and print everything again. So that is the end of the list presentation. And yeah, I can recommend doing your Zybooks, looking at the code, and just kind of working through it with paper if you want to learn more. Thanks for watching.